Alright, we're making sure the audio works. I have my early bird already. I have my early bird up there. Let's see if I have everything I need. Where's my black marker? There it is. So the question is, can you hear me now? And then can you read my haiku and my binomial, my early bird? Normally this would be my early bird in the morning, so students would get there at about 9 o'clock and start working on the early bird. But unfortunately, we're now away from home. So we'll get it started with this early bird this morning and then lead into the lecture as always. Mr. Simpson, can you hear me? Hey, Fernando, can you hear me? Can you hear me? Good morning, good morning. Yay. Sound check. Sound check. Yay. Yay. That's right, introduce yourselves. Mr. Simpson's going to keep a tally who all's on, who all's leaving comments so that I can get bonus later. So normally we would have an early bird in the morning, and here's our early bird for the morning. We're going to use it here in a minute once we get everybody in class, just like always, but you can start thinking about it, warm up your brains with it. So think about that, classical probability. Man, I got to warm up my brain too. Think about that classical probability that we did before. How would you go about doing this problem? Put it in words first. Hey, Lily. Yay. Hey, Eve and Lily and Fernando. Way to join class. Y'all are doing great. Fantastic. Way to be here. Come on in. Let's start warming those brains up. Start thinking about that problem. Just from what we did last time. It's not quite 9:30 yet, so we'll give it a couple more minutes as y'all think. Hey, Josh, how's it going? We're here this morning, wide awake, bright and early. Hopefully y'all are still social or physically distancing from others. I had to brave the grocery stores this weekend, so I'm hoping that I stayed far enough away. But if I got it, then that means that this disease is more deadly or more contagious than what we're thinking, because I was super careful. Fernando, did you walk into the wrong class again? That's hilarious. Hey, Amani! Hey, Alyssa! Yay! So here's just a warm-up, just like we would normally have in the classroom, just to kind of get your brains going, start us thinking about what we're doing. You can see that this is pretty much what we did last week, but it's going to tie into today's as well. It says you play a game where we roll a die 3 times. You win if you roll a 4, and you lose if you roll any other number. What is the probability of winning 2 out of 3 rolls? So as you're thinking about it, put it into words and comment while people are coming in. Go ahead and put it into words how you would find the probability. So think about using those conjunctions of and or, just like you did last week for that classical probability. Put it into words for me, and then we'll look at the probability here in a minute. And then my son and his haikus, I rewrote it for him a little neater and off to the side. But he says, be patient for now. A life spent on fast forward skims through the best parts. So right now, as we're physically distancing, we can take a little more time to just enjoy our life and, just take it easy. Take it easy. And enjoy each little piece of it. Somebody told me one time that when we start looking forward to Friday, that we're missing out on the rest of the week. It's like you're trying to wish away your life to get here faster. So that's exactly right. Just take each day and enjoy each day that we're here. Way to be. I like it. Eve, that's a good first way to do it, is not 4 or 4 or 4. Because I want to roll 2 4s. Can you think of another way? So, and remember, it would be not 4. I'm rolling them at a time, all at the same time. So it's not 4 or 4, but not 4 and 4, because I'm going to roll all 3 of them. So it'd be a not 4 and a 4 and a 4. See if you can come up with the other ways, with the ors in there. There you go, Lily. 4 and not 4. Oh, that second one, I like the first one, 4 and not 4. Or on your second one though, 4 and not 4, we only rolled 2 die. I need to roll 3 die in there. Good morning, Aunt Carrie. Good morning. Way to be here this morning. Good job. We're just warming up with an early bird here on the trying to come up with our probability for rolling it 3 times, and we've got a good start. So I think we'll go ahead and get started. Does she have it? And not 4 and 4. Oh, she does have it. 4 and not 4 and 4. I didn't read that 4. Good job, Lily. Good job. You have it. You have it, Lily. You're right. You have it. My old eyes trying to read those comments. Okay, so I like that exactly. So we have 4. So let me see if I can read them here. It says 4 and not 4. So that was a good warm up here from last time. If I'm rolling the dice 3 times, I'm going to have 3 entries. And I want to win 2 out of the 3 rolls. Well, that means 2 of my rolls need to be that 4. So Lily's got it here, 4 and not 4. Or that was one of the ways. Another way to do it would be to say 4 and not 4 and 4. So 4 and not 4 and 4. Or that last way to do it would be 4, not 4 and 4 and 4. So not 4 and 4 and 4. So now let's put the probabilities with that. So what would be the probability that I would roll a 4 on a 6-sided die? You know, how many sides are there? That's going to be your denominator, and then the how many 4s are on the dice? That's going to be your numerator. So yeah, the probability that I roll this then would be 1 out of 6. The and tells me to multiply. The probability for getting a 4 here is 1 out of 6. The and tells me to multiply. And then how many not 4s are there? So what's the probability of not getting a 4 or of not a 4? Well, if the probability of getting a 4 is 1 out of 6, then the probability of not a 4 would be 5 out of 6. All right, now I'm going to add, and I've got 1/6 and 5/6 and 1/6. Notice that each time I roll that die, you got it, you're on fire this morning, Lily. You've had more coffee than me, obviously. Perfect, that's exactly it, Eve. Okay, so as I roll that dice, every time I roll it, the probability that I roll a 4 on each roll is going to stay the same. It's going to be 1 out of 6. And the probability that I don't roll a 4 is going to be 5 out of 6. So here I've got 5 out of 6 and 1 out of 6 and 1 out of 6. So Eve wrote this down, this probability, But notice that there are 3 different ways. Good morning, Giselle. 3 different ways to do that. You know, 1, 2, 3. So once we find this probability, we can just multiply it times 3. And we saw that last week when we were doing the classical probability, that once we found one of the probabilities, it was easy then. We just needed to know how many ways to do it. And in this case, there were 3 different ways to do it. So I could just take that 1/6. And the reason I'm doing 1/6 twice there, you know, 1/6 times 1/6, is because I want 2 wins. I want 2 of those probabilities that I roll a 4. You know, I need 2 of those. And then that failure or that other thing is going to be 5 out of 6. And you're exactly right. We're just going to take it and multiply it by 3, because once I have that probability, I know it's the same thing over and over again. I'm just multiplying it times 3. Now, by the way, let's talk these tasks for just a minute. So I graded all day Sunday and got all your tasks graded. And there were several of you that didn't turn anything in. So in order to pass, you got to earn some points. And I'm glad you're here. Be here in class. But then also I need you to do the tasks and turn them in. So make sure you're getting stuff turned in. And remember that the due date is Saturday by midnight so that I can grade all day Sunday. That's the plan. So you guys you have to get those tasks done. So the plan is right after this class, I'm going to sit down at the Discord and I'll be available to help you until 2:30. I'll be there unless I'm going to the bathroom or something, you know, away for a second. But even then, there'll probably be another Simpson on. At 2:30, from that point on, it may be a little spotty because I have to do things like go check on my dad and make sure he's okay, and you know, little errands around the house. But even then, I'll be off and on Discord because I can walk around a lot of times with my headphones and still help you. So you know, just come join us on Discord, do your homework right after class, and be done with it so you don't have to worry about it. So that's the plan. And then each day we'll do that. And then that way on Fridays and Saturdays, I can be making the videos and preparing for next week. And then on Sundays, I can grade all day. So if you guys will get your homework done Monday, Tuesday, Wednesday, Thursday, then on Friday, Saturday, I can make videos, and on Sunday, I can grade. And if not, I mean, you guys can use that discussion. Y'all were doing a great job of using the discussion in Discord where you were helping one another. That was fabulous. So keep that up. So yeah, but definitely y'all get your, I mean, maybe you were trying to make it easy on me by me not having to grade as many, but I don't like that. I want to be grading all day Sunday. So turn in your tasks. Actually turn them in early, and if they're wrong, I'll give them back to you this week. And then you can return them in, so to submit them with the corrections on it. So, you know, get it done each day, turn it in, and then that way you can make sure that you're getting all the points that you possibly can. I want to make it through this. Okay, so here, one of the things I noticed on the task is some of you weren't reducing. So, you know, you're making it difficult on yourself where you're just multiplying these big numbers and you're not reducing as you go along. So I'm going to look for any reduction that I can as we go along. So for instance, here I have a 3 over a 1. Remember when I would multiply straight across, but I can do some simplification here because 3 goes into 6 2 times. So instead of multiplying across and then figuring out how to reduce, now I look. The only thing I have on top is a 5. This is not going to simplify further because 5 doesn't go into anything down here. So now I can multiply, and I've got 5 times, well, that's 36 doubled, or 72. So the probability, we find this probability of 2 wins and a loss, we find that once. But we know there are 3 different ways to do it, and so that 3 different ways, we just multiply it by 3. Now this leads in perfectly to the binomial distribution, which is what we're going to learn about today. In fact, You've already done it. You've been dealing with binomial distribution. You've just been with brute force figuring it out, because you would have to figure out all these different ways when we did the classical probability. In today's lecture, where we deal with binomial, the formula gives you the number of ways. In fact, remember back to the counting when we talked about combinations and permutations? This is really a combination problem. I'm looking at how many ways, remember those words? I was like, this is accounting when it says, how many ways can I get 2 wins out of 3? And y'all found that, but we could also use counting to help us to find out how many ways. Notice that here, where we rolled the 4s didn't matter. The order didn't matter. And so when we did order didn't matter, you remember what were we using when order didn't matter? What was that when order didn't matter? Oh, we're going to use some Pascal's triangle later. We're going to learn all about that Pascal's triangle later. So, and how it helps us with using a yeah, send it again, Amani, because you're right, I did not see it. Send it again because I did not see it. But hey, we got to make sure we're friends. That was one of the things I noticed with others, that if we weren't friends, I couldn't see your video. So make sure you tag me and make sure we're friends. If we're not, send me a friend request so that I can see your stuff. Okay, so here the probability. Oh, I was talking combination. This is a combination because order doesn't matter. And I'm going to show you how that's a combination. You know, I'm rolling it 3 times. So we have 3 things, and we are choosing 2 of them to be wins. So here, to find out the number of ways, we can do 3 choose 2. So you remember that combination and how order didn't matter? So when we're trying to find out how many different ways there are, we can use combination when because the order here doesn't matter. And we're rolling it 3 times, and we want 2 of those to be wins. I'm going to show you how that gives us this how many ways that we have. So let's go back and remind ourselves 3 choose 2. That formula, you put the 3 factorial on top. On bottom, you do 3 minus 2 factorial, and then the 2 factorial. And like Mr. Simpson said, we're going to learn later to do Pascal's triangle. Pascal's triangle is going to help us with these combinations. So here, 3 factorial. Well, I'm going to do the bottom first so that I have 1 factorial and 2 factorial. So I can stop at 2 as I count down. 3 times 2 factorial. Well, this 2 factorial and that 2 factorial become 1. This is just 1, so 3 divided by 1 is 3. Notice there were 3 different ways for us to get 2 wins. And sure enough, that's exactly what I have, is 3 different ways to get that. So the combination is going to tell us how many different ways. And then, because we wanted 2 wins, we used that probability twice, and then we had this failure of not a win, and we used that once. Now I'm going to show you the binomial formula and how all this fits in. So y'all got all this, and here it goes. There goes our early bird. I'm probably going to need this in a little bit, but here it goes. All right. So the binomial distribution, the formula looks like this. The probability of some x is going to equal this combination. Now, by the way, we wrote combination as 3 choose 2. I can't remember now if I showed you this notation or not of 3 choose 2, but this means the same thing as that. Here we are doing a combination of 3 choose 2. Notice there's no vinculum here, there's no line there. It's just this notation without that line tells me I'm doing a combination. 3, choose 2. So I'm going to put some letters in here, some variables in here, but this is just going to tell us that we're going to have a combination to begin with that's going to tell us how many different ways we can have our number of wins. Then we're going to multiply that times the probability for success, or the probability for those wins, multiplied by itself that many times. So think about it here. We did the combination there. Then we took the 1/6 and we multiplied it by itself twice. So let me just show you in this one. Our x was 2 because we wanted 2 wins. Then we did this combination of 3, choose 2, the number of times we were rolling it, and how many wins we wanted. And then we multiplied it times that 1/6, that probability for success, the 1/6, we did that times itself 2 times because we wanted 2 wins. So we squared it because we wanted 2 wins. So here, this is what that says, is we're going to take our probability for success and just multiply it times itself, however many of those wins we want. And then this 5/6 is the probability for failure or not wins. Well, how many of those did we need? Well, since we were rolling it 3 times and 2 of them we wanted wins, well, there was 1 time that we didn't want to win. So we're going to use this Q to let us know that that's the complement of our P. And then to find this, we're going to do n minus x. So I feel like I jumped into the formula a little bit early, but you got the idea here with the formula where it's coming from. So now let me back up just a minute and tell you a little bit about a binomial distribution. In order for us to be able to use this formula, there are certain things that have to happen first. Number 1, we have to have 2 outcomes. You see that binomial? So there are 2 possible outcomes. 2 possible outcomes. Or we can put them into groups that are 2 outcomes. So, we wanted a 4, and then there are a lot of different numbers on the dice, but we made it into 2 groups. We said 4s and not 4s. Those stayed the same, 4, not 4. Those were our 2 different groups. So you've got to have 2 possible outcomes. We're going to call one of them successes, and we're going to call the other ones failures. So we have our successes and our failures. You did that in your tasks when you split it up into black and white. You may have had a bunch of different colored M&Ms or starbursts, or maybe you had pens, markers, but you split it up into pens and markers, or pink and not pink, or whatever it was you were doing. You did that. So we are going to have, in order to have a binomial, you have to have 2 possible outcomes, a success and a failure. Then the second thing that has to happen is our probability must remain the same. So the probability must remain the same. Probability, let me switch hands. Probability must remain the same. So the probability for success has to stay the same each time. Think about when we roll that dice, it's always 1/6. Now think about your 2 tasks that you did. In one of them, the probability stayed the same every time. But in the other one, the probability didn't stay the same. Hey, Brandy. Hey, Bo. Bunch of y'all have added back. Hey, Adam. Tashara. Yay! We got lots of people joining. Way to go, guys. Way to be here in class. Okay, so here the probability must remain the same. And so in those 2 tasks you did last week, one of them the probability changed, and one of them the probability remained the same. So that probability that it remained the same was with replacement. Remember when you put it back in? So in this one, you can kind of think of as with replacement, but not always, because like in this case with the dice, we're not replacing anything. Each one of those dice rolls is just independent, and every single time the dice, the roll of 4 is 1/6. It just stays the same on each one of them. So, now, number 3, third thing that has to happen is we have to have a fixed number of trials. Fixed number of trials. And all I mean by that, when I say a fixed number of trials, I just mean that we're going to roll the dice a certain number of times. So I'm not just going to infinitely keep rolling the dice over and over again. We said we were going to roll the dice 3 times. Or when you were drawing from the marbles from the bin, you drew 3 marbles out of the urn. So there's going to be a fixed number of trials each time. Okay, so these are the conditions that have to be met in order for it to be a binomial. You have to have 2 outcomes. Each one of your things must be independent, and so therefore the probability must remain the same. Or you can kind of think with replacement. And then we have a fixed number of trials on each one of these. If we have that set up, then we can use a binomial distribution. We can use this formula. Now let me tell you about these letters that are in here. So what are these variables? Well, let me start with the n. The n is that number of trials, equals the number of trials. So think about over here, we were rolling it 3 times. So we rolled that dice 3 times. And my experiment was rolling the dice. I rolled it 3 times. So that n is just the number of trials. The x is the number of successes that we want. So that's the number of successes that we're trying to get. So here I wanted 2 wins. So that's the number of successes that I want. Then my p is the probability of that success, the probability of success, which remains the same every time. That's one of the conditions there. So the probability of success is my p. And then my q is the complement of p. Or you could say 1 minus p to get that probability, or you could just say it's the probability of failure. Probability of failure. But if you're having trouble with coming up with what that probability is, it's just going to be 1 minus your probabilities for success. Notice we didn't do 1 minus 1/6 to get the 5/6. We just said, well, what's the probability that we don't roll a 4? And we knew that it was 5/6. But notice also that this 1/6 plus 5/6 gives me one whole thing. That's all of the outcomes that could possibly happen from rolling a die. So here is the binomial formula that we're going to use throughout this lecture today. And we're going to see that we did this without the formula. We figured it out without the formula. The formula just helps to move it along a little faster for us. Okay, let me give you some examples. So, here's where maybe I missed my document camera, but to help me out, I've devised a way. Let's make sure y'all can see this. And these are going to be the questions that we're going to work on today. Let's just make sure that the things a teacher has in their house. All right. I don't know if you can read it or not, but I'll read it to you. Maybe you can. It's awfully little. But I'll go ahead and read it to you. It said, the first one we're going to do is, you are taking a multiple choice quiz that consists of 5 questions. So on the test, picture what's going on. So on the test, there are 5 questions on there. Each question has 4 possible answers. only one of which is correct. So, you know, each one of your questions has 4 answers. This guy is correct. Find the probability. To complete the quiz, you just randomly guess. You had no clue what any of the words on there are saying. You're just randomly guessing. Maybe you even roll a dice to help you figure out, you know, a 4-sided dice to help you figure out which answer you're going to put on there. Or use a number generator or something to help you. You are truly randomly just guessing to the answers to each of the questions. And I want to know, what's the probability that you get exactly 3 answers correct? You know, 3 out of 5 would be a 60%. That would be a D, be passing. So I just want to pass. I want to know, what's the probability I get exactly 3 correct? So first thing we want to do is just see, can we use the binomial? Yeah, always use D. Always pick D, sure, or B. Or you could use a number generator to help you out. Maybe the number generator knows something you don't. So anyway, we're going to do exactly 3. But the first thing we have to do is figure out, is this binomial? So does it have 2 outcomes? That's our first thing we have to figure out. So you tell me, do I have 2 outcomes to this question? So as I'm answering each one, what are my 2 outcomes? D is passing at Temple College, but you're right, it probably doesn't transfer for you, so you probably need a C. So, you know, make it to 700 points, which means you need to turn in your tasks if you're going to make those points. Y'all get those done this week. Oh, good, Brandy, perfect. It's either wrong or correct. Those are your 2 outcomes. It's either going to be right or wrong. Those are your 2 outcomes. All right, so we have the 2 outcomes. Check. Next thing we need to know is the probability the same every single time? So what is the probability that I get a correct answer? So we know that there are 2 possible outcomes. Those 2 possible outcomes were right or wrong. Now, I want to know, is the probability the same? Is the probability the same each time? So what is the probability for getting a right answer? Perfect. It is 1 out of the 4 answers is correct. So the probability does stay the same for each one of the questions. And do we have a fixed number of trials? In other words, are there a fixed number of questions on my test? So that I'm not doing an infinite number of questions. Is there a fixed number of questions? And if so, how many trials are there going to be? So we have 5 questions. So there are 5, so it's a fixed number of trials on there. It meets all our conditions, so therefore we can use this binomial formula. So now it's just a matter of figuring out my variables and plugging it into the formula. Now's the no fun stuff. This is just the tedious stuff, so let's do this. Our n, our number of trials, is 5. You've already told me that. That's our number of trials. Our x is, well, how many ones? Let's answer Mr. Simpson's questions first. So what is my Q? If my probability for success is 1/4, what's that probability for failure? What's the probability that I get it wrong then? Good, 3/4. Perfect. Because there are 3 wrong answers out of every 4. And notice that 3/4 plus 1/4 makes the whole thing. They are complements of one another. Then, how many of these do I want to get right? How many successes do I need? Or how many successes do I want? So we go back and look, and I want to get exactly 3 answers correct. So my number of successes here is 3. Now it's just a matter of putting it into the formula, or even thinking through the formula. Man, y'all are doing great this morning. Y'all are on fire. All right, so thinking through the formula. What we want first is, how many different ways can I get it right? You know, I could get the first one right, and then get the second one right, get the third one right, and then wrong and wrong. Or I could get the first one right, the second one wrong. I don't have to go through all those possibilities. We know that we can find out the number of possibilities by just finding a combination. We have 5 trials, 5 different questions, and we want 3 of them to be right. So we have 5, choose 3. So that's where that combination comes into play. It's just telling us how many different ways there are that can be right. Then we're going to look at the probability for success. So we do our probability, that 1/4. You know, if I'm doing it's right and right and right and wrong, or, you know, there are this many, however many that combination is, different ways to do that. I'm going to find the probability for that right. Well, how many times am I going to put that down? 3 times, because that's how many successes I want. So I'm going to do 1/4 to the 3rd power, 1/4 times 1/4 times 1/4. Then I'm going to multiply that times the probability for failure. Well, y'all told me that that was 3/4. The probability I get it wrong is 3/4. And how many of those wrongs do I need? Well, if I do 3 rights, that means that there are 2 left over that need to be wrong. Or we're going to square it. So you see how doing this classical probability that we did last time, this is just going to make it a little bit easier because I'm not going to have to come up with all the ors. The combination is going to tell me how many different ways there are for me to do it. But I still do need to be able to think about, you know, what is the probability there that I'm coming up with each one, or the probability of my successes and my failures. All right, so here's what we're doing. We're finding the probability of exactly 3. Now I'm going to do some arithmetic. This is my combination. Notice I did not draw a vinculum. If you guys don't draw a vinculum on there, there's no line there. It's just 5, choose 3 here. On top I have 5 factorial. On bottom I have 5 minus 3 factorial. And then 3 factorial. Remember, that's that formula for the combination. Now this cubed means I'm doing 1/4 times 1/4 times 1/4 times 3/4 times 3/4. I'm going to keep going in a linear fashion. I know a lot of you guys like to take a piece of it and go off to the side and work off to the side. I don't know, it makes it really hard to stay organized that way. It might be better just to go in a nice linear fashion so that you can follow from step to step. So here, I'm going to keep going. This 5 factorial, well, on bottom I'm going to have 2 factorial and 3 factorial. So I'm going to stop at 3. 5 times 4 times 3 factorial. This 3 factorial and that 3 factorial become 1. This 2 factorial is 2 times 1. Well, notice that 2 times 1 is just equal to 2, and that goes into 4 2 times. So I'm going to go ahead and simplify there. So all I have left on that is 5 times 2. And I'm multiplying that times this 1/4 times 1/4 times 1/4. Oops, 1/4. Times 3/4 times 3/4. I'm going to keep it together. 1/4 times 1/4. And y'all are like, why don't you just multiply it out, Miss Simpson? I'm trying to get y'all where you will simplify first. So you're right. There are 10 different ways for us to come up with, to do how we could get 3 right and 2 wrong. Now think about when we were having to do the classical our lesson last week, to have to come up with all those 10 possibilities. Man, that'd be a lot, wouldn't it? So this just makes it a little bit easier for us to know there are 10 of them. Then I'm going to show you, I'm going to simplify here before I multiply. Again, this will help us not have to reduce later. And a lot of you missed out on reducing at various points in the assignments. So you want to make sure before you multiply, look for any reduction. Notice that these guys are up on top. So this 2 can go into that 4 2 times. So now 5 can't go into 4 or 2, and 3 can't go into 4 or 2, so I know that I can't reduce it any further. So now I just have on top 5 times 3, which is 15, times 3, which is 45. And on bottom, I have 4 times 4 times 4 times 4. That's 4 to the 4th power, which is 256. You know, this is 16 times 16, which gives me 256. Double that, and you've got 45 over, well, that's 12, carry 1, 10, 11, carry 1, 4, 5, 512. So the probability that I get exactly 3 right is 45 over 512. You know, if you wanted to find out about what percent that is, remember percent is out of 100. So we'd be dividing it by about 5, a little bit more than, 5. But we'll go with 5 because that will get us close. We can approximate that way. If you divide the bottom by 5 to get down to 100, then you divide the top by 5 to get down to 100, and it's about 9%. I know nowadays y'all are at home and you have a calculator, and I can tell that some of you are just using that calculator. So make sure you're showing me the work, but you can see, we can approximate that. It's about 9% of the time we're going to get exactly 3 correct. We're going to make that 60 on there. Yeah, the odds of someone who's not doing their homework are not good. You got to start doing it, guys. All right, now I'm going to take this same question and I'm now going to look at least 1 correct. What if I want to get exactly 1 correct? So what changes on here? Well, first of all, what does it mean to be at least 1? So if I'm doing at least 1, then, if the doctor tells me to put at least 1 bandage on the patient, how many bandages am I going to put on there? So for just a second, I'm going to make this disappear. And let's just think about for a minute, how many different, in this problem, how many different outcomes are there? Like how many could I get right? Let's think about our probability distribution. And y'all did this, y'all created, probability distributions in this last task. So think about your possible outcomes. If I've got 5 questions, how many could I get right? Well, I could get 0 right, or I could get 1 right, or I could get 2 right, or I could get 3 right. I'm going to stop somewhere on there. I'm going to stop at 5. Good. And you're right, at least 5, at least 1 correct means that I'm going to get 1 right, or 2 right, or 3 right, or 4 right, or 5 right. This is at least 1. So to find out the probability that I get at least 1 right, I'm going to do 1 or 2 or 3 or 4 or 5. In other words, I would have to do this formula 5 times, like this. I would have to say the probability, oops, maybe I didn't mean to erase that. The probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 5 to get at least 1. That means I'm doing the formula 5 different times. Can you think of an easier way, maybe another way that we could do this instead of doing the probability of 1 plus the probability of 2 plus the probability of 3? When I start having to do that much work, I start thinking about the complement. So could we use the complement here? And if so, what is our complement? Yay, y'all got it. So, Bo, you're close, but at most one includes the 1. most 1 is 1 or 0. You know, if my doctor tells me to put at most 1 bandage on there, I can put 1 on there, or I can put 0 on there. But notice that these two overlap. So they're not complements of one another because they overlap with one another. So look at this at least 1. What's missing from the group? What is it that's missing from that group? Notice that just the 0 is missing. So the complement of at least 1 is just 0. Complement of at least 1. And notice that together they make up the whole set. So the complement of at least 1 is just 0. So instead of finding all this, let's just find the complement of it. If we add the probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 5. In other words, if I want to know how probable is it that I get 0, 1, 2, 3, 4, or 5 correct on the test, well, one of those things is going to happen. It's 100% sure that I'm going to have one of those things happen. So this whole set equals 1. So what I'm going to do is I'm going to find the probability of 0 and subtract it from that 1. And then that'll give me the probability of at least 1. So notice here I've got 1. If I subtract the probability of 0 from both sides, it gives me this probability. It's going to leave me with just that part. So that equals 1 minus the probability of 0. So to find the complement, I'm just going to take one whole thing, the whole set, and subtract that probability of 0. Maybe this helps us to visualize better that whole complement idea. So let's do that. Let's find the probability of 0 and then just subtract it from 1. So if I'm finding the probability of 0, well, my fixed number of trials is still 5. But the number of successes I'm looking for is now 0. The probability for that success stays the same. It's still 1 out of 4. And the probability for failure is still 3 out of 4. So the only thing that changed there was my number of successes that we're looking for. I'm going to erase this so I can do the formula now. So now we just plug it into the formula. We say the probability that I want 0 correct. Well, how many different ways can I get 0 correct? You know, if I'm doing the problems, well, you can kind of think about it. The only way I can get 0 correct is to get it wrong and wrong and wrong and wrong and wrong. All 5 of the questions have to be wrong in order for that to happen. So here I'm going to multiply that times my probability for success. How many times? 0 times. I'm not going to multiply times the probability for success. I didn't get any correct. Which means I got 5 of them wrong. So I'm doing the probability, you know, think about it as wrong, 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 and wrong, and wrong, and wrong, and wrong. Well, I would multiply this times itself 5 times. So now, how many different ways are there? Well, 5 choose 0 is 5 factorial over 5 minus 0 factorial. 0 factorial. We're going to look at the Pascal's triangle tomorrow, and we'll get really fast at being able to do some of these combinations. Plus, just the more you do it, the faster you're going to get at it. Remember, anything raised to the 0 power, any of our probabilities here raised to the 0 power is just going to equal 1. Non-zero number raised to 0 power is 1. And then this is 3/4 times 3/4 times 3/4 times 3/4 times 3/4. Now, this is 1. So on top here I have 5 factorial. Remember, that's just equal to 1. On bottom here I have 5 factorial. So again, that's just equal to 1. So I just have 1. There was only one way for me to get them all wrong. I had to do wrong and wrong and wrong and wrong and wrong. There was only one way to do that this time. Times that 1 just gives me 1. So really all I'm left with is this 3 times 3 times 3 times 3 times 3. So 3 to the 5th power, well, that's 9 times 9 is 81 times 9 is 729, I think. Somebody could check my math there. And here I've got 16 times 16 is 256 times another 4, I think, is 1024. So the probability that I get 0 right is 729 over 1024. But I wanted to know the probability that I got at least 1. So that's this probability, that's this probability of 729 over 1024. But now I wanted to know this probability, that I get at least 1 right. So what I'm going to do is take this and subtract it, because all these guys should add up to be 1. So I'm going to do the probability at least 1, so it's 1 or bigger. I do 1 minus that 729 over 1024. Remember, 1 is just this denominator over itself, because I have to have a common denominator. When I'm adding, I must have a common denominator. And then I subtract the 729 over 1024, and you guys tell me, wait, did I do that wrong? Oh. 9 times 9 is 81. Oh, it sure is. It's 243. Darn it. So this is 243. I don't know what I was multiplying. You're right. You're right. Just making sure you're with me. I was just making sure you're here with me in class. Way to be on top of things. Great job. So now I'm subtracting that 243. Good job. Good job. I don't know where I came up with 729. I was really just testing y'all. That's what that was. Now I'm going to subtract. So this minus that 243, because I want the probability of the full set minus that. Let's fix it here too. This is wrong too. 243. So now do that subtraction and just tell me what it is so I don't have to. So 1024, that's the part of the classroom environment I'm missing out on, is y'all do the math and tell me, so then I'm not doing it. That's 1, 12 is 8, make that a 9. So now maybe that's 781, see if it really is. Yay! Or maybe it's 8, wait, which one is it? Yeah, it's, I think it's 7. I think we got a bar there. Okay. So this is the probability that I get at least 1 right. Now, let's look and see. That last little bit with this question, I just want to know what's the probability that I get less than 1 correctly. Or less than 1 correct. What's the probability I get? These guys are weird. Answers, why didn't it just say correct? Less than 1 correct. Well, in order to get less than 1 correct, I only want to get 0 correct. That's less than 1. You know, anything less than 1 is 0. We already found that probability. It was 243 over 1024. So notice that this is also just less than 1. 0 is the only thing less than 1. And that's the complement. Less than 1 is the complement to at least 1. Complicated. All right, so there's an example of using that binomial. So we don't have to go through that whole classical thing. Instead, we can just use this binomial if the conditions exist. So let's look at this next one and see if the conditions are met on this one. So a surgical technique is performed on 6 patients. You are told there's a, what is the probability here? I erased it. I think it's an 80%. 80% chance of success. Find the probability that the surgery is successful for exactly 4 patients. So, in other words, you're going to go in and do a surgery, and you know that there's 80% chance that there's going to be success, and the doctor's performing 6 of those. He's going to do it on 6 patients. You want to know what's the probability that exactly 4 patients have a successful surgery. So let's think first, is this binomial? In other words, are there 2 outcomes? That's number 1. So are there 2 outcomes to the, I know, right, Adam? I'm not sure I want that doctor performing this surgery on me. 80% of the time, that means 20% of the time. That means 1 out of every 5 patients is not successful. I guess it depends on what the surgery is, though, on whether I want it done or not. So, yes, it does meet those conditions, the 2 conditions, because we have success or failure. Either it works or doesn't work. Then, what about, is there a fixed probability? In other words, does the probability stay the same each time? Yes, it's an 80% chance for each person going in that their surgery is successful. And then the last thing, so there's 2 outcomes, the probability stays the same, and then the third thing, is there a fixed number of trials? That's kind of where I go to, Eve, is the life or death. And there are a fixed number of trials. He's not going to do this infinite number of times. He's got a fixed number. He's doing it with 6 patients. So our conditions for binomial are met. We have 2 possible outcomes, life or death. Maybe it's not always life and death. Maybe it's vision or not vision. You know, my dad just had eye surgery. Maybe it's to be able to see or not be able to see. Or maybe it's, to be able to walk or not be able to walk, whatever. But success or failure. The probability for success does stay the same. My probability each time is 80%. So I have that 80% probability. And there are a fixed number of trials. There are 6 patients that we're going to do this on. So there are a fixed number of trials. So now, let's go through the formula. So you told me my n, which is my number of trials, is 6. You told me my probability for success was 80%. We could write that as 80%. I could write that as 80%. Or maybe I write that as 80 over 100, which of course simplifies down to 4/5. Now, if my probability for success is 4/5, what's my probability for failure? Or what's the complement to that? What is my probability that I fail? The complement to that. Good, that's just 1/5. You could say 20%, because 80% plus 20% makes 100, but that, again, is just 20 over 100, which just reduces down to 1/5. Notice, 4/5 plus 1/5 makes the whole thing. Good job, guys. So that's my complement. Now I have to figure out my x. And my x is just the number of successes that I'm looking for. So in this case, I want to know the probability that I get 4 patients are successful. So my x value, my random variable here, is going to be 4. Just for a minute, let's look at the probability distribution, or look at the random variables, the possible outcomes. You know, if he's got 6 patients, he could have 0 success, he could have 1 successful patient, he could have 2 successful patients, he could have 3 successful patients, 4 successful patients, 5 successful patients, or 6 successful patients. So those are the different outcomes that he could have. 0, 1, 2, 3, 4, or 5 or 6. We're going to find the one for 4. For exactly 4 is what we're looking for. All right, so let me put the question back up here for you. So exactly 4. And Adam, you are exactly right. First thing we want to know is to find out how many different outcomes, you know, which ones of those patients are the ones that live and which ones die. So 6 choose 4, how many different ways could that happen? Then we're going to take this 4/5, that probability for success, and because 4 of our people are successful, we're multiplying that success times itself 4 times. Or you can think of this as to the 4th power. Then we take our probability for failure, and that means that some of the patients are not going to be successful. Well, if 4 of them are successful, then how many are not successful? Well, it's got to add up to be that 6. So what plus 4 is going to give me 6? That means that 2 of our patients are not going to be successful. So 4 are successful and 2 are failed. Now it's just a matter of doing the math. Again, I'm going to show you how we can do it nice and neatly on here. So that we have 6 factorial over 6 minus 4 factorial times 4 factorial. Then you've got 4/5 times 4/5 times 4/5 times 4/5 times 1/5 times 1/5. I'm going to do it in a nice, neat, linear fashion. So this is going to be 2. So I'm going to stop at 4 factorial on top. 6 times 5 times 4 factorial. This 4 factorial and that 4 factorial become 1. 2 times 1 is just 2. So 2 goes into 6 3 times. I have 4/5 times 4/5 times 4/5 times 4/5. This is what y'all don't want to do on your papers. You don't ever want to write it down over and over again, but I want you to. Feel free to do it. That way you won't make as many mistakes, and it'll help you to reduce later. Then here, notice there's a 5 on top and a 5 on bottom. So instead of multiplying all this out first and then having to reduce, I'm going to look for those reductions to begin with. And here I've got a 5 on top and a 5 on bottom that reduces. I mean, this is enough work multiplying without having to do it a little bit more. Now this 3 doesn't go into any of the 5s, the 4 doesn't go into any of the 5s, so now I can just multiply it out and know for sure that it's simplified. So here I have 16 times 16, which is 256. 256 times 3 is, I don't know what 256 times 3, how about 256 times 3 is 512, is that right? No, 256, 6 times 3 is 18, that's not quite right. What's 256 times 3? What is 256 times 3? You'll help me out with that. And then this is 5. This is 25 times 25, which is 625 times another 5, which is 3,125. So 3 times 256 was 18, carry 1. 15, 16, carry 1. 3 times 2 is 6, 768 maybe? Oh, I like it, 768. So we've got 768 over 3,125 is the probability there. Now, I want to know what's the probability of at least 4 patients. So let's go back and look again. at this. We found the probability of 4 patients. But what about if I wanted the probability of at least 4 patients? So in other words, if I'm going to do at least 4 patients, which ones am I doing here? At least 4 means that I'm going to do a 4 or a 5 or a 6. So all of these are at least 4. Notice that doing the complement here is not going to be any easier, because the complement of 4, 5, 6, what is that complement of 4, 5, 6? What's the rest of the set to make that complement? Yeah, is 0, 1, 2, and 3. So this is the complement. That would actually be more work this time. So this is the complement of at least 4. So being able to write out your outcomes sometimes helps you to find that complement. Again, Bo, not that at most 3, because at most 3 means, oh no, I agree with you. Yes, you're right. At most 3 is 3 or less. So yeah, we could say at most 3. Good. At most 3. Yes. Yes is the complement. You are correct. Sorry, my bad. You are right. Good job. Okay, so here's what I want you to do. Now look, now that we've got it set up and we kind of have this idea, you know, I've been not letting you use calculators this whole time in class, and part of the reason is I want you to get good at being able to do this arithmetic. And you're still going to need to do that. On the tasks that you turn into me this week, you are going to need to show, or the homework or whatever, I want to see your work. I give you the answers. You have to show me how you get there. So I better be able to see your work. But I am going to tell you about an online resource that the rest of us might use if we were doing a probability like this. So if I were doing something where I was having to do the probability of 4, probability of 5, probability of 6, I was doing this binomial distribution, I would go to Matt Bogner's page, and Mr. Simpson's going to link it on there for you. He has a binomial distribution calculator. You can also use this maybe to check your work. Play around with it, and you can see this calculator online where we put in our probabilities and our, as long as we have our fixed number of trials and our x and our probability, then it'll give you the answers or the probability for that. So here's your job, because we're now out of time. Your job is to do this. Go to that calculator online, go to Matt Bogner's calculator, and I want you to find the probability for this problem of successes of at least 4 people being successful. And he's going to tell you where to find it there online, and use his calculator to determine the probability of at least 4. Or you could just, you wouldn't have to use the calculator, you could just brute force it like we did, and know that you're just going to now find the probability of 5 and find the probability of 6 and add it together. Do that one and add this problem to the binomial distribution homework, and I'll give you bonus points for it. All right, guys. Your job is to go right now, start on the binomial distribution homework. You may not be able to finish it all because we're going to work some more tomorrow on binomial distribution, but get as much of it done as you possibly can today. And then tomorrow we'll look at the expected value and the standard deviation of binomial. So we'll do that tomorrow. So when you get to those problems tonight and you're a little bit confused, just hold off and we'll do those tomorrow. Turn those tasks in earlier rather than later. Got it? Into Dropbox. Get it done. Don't miss out on points. And I'll see y'all on Discord as soon as I end this. Come join me on Discord. Yes, under discrete distributions. Oh, this good question, Bo. This is a discrete distribution because notice that all of my outcomes are discrete variables. They're countable. I can count the number of successful patients. I can count the number of 4s I got. So they're called discrete distributions because our random variable is countable. I'm glad you noticed that. But if you can't figure out how to use that calculator, then you can just brute force it. Turn that one in and I'll give you bonus points. All right, come join me on Discord. Math made simple at Simpson Math. Bye guys.